from a triple bond to a single sigma bond. So I've lost 2 pi bonds. This would be an addition. As an addition reaction, both H2 and Br2 would work, but also so would HBr. Because in that addition situation, I've got resonance systems where we're generating positives and negatives across that pi bond. And HBr would also generate that positive and negative across that pi bond. Okay, as reagents, that would potentially allow me to look at that. So I could go through and take a look at my answer choices. This does look pretty suspicious, like A is valid. The last thing that would make me hold up and be, what do I need to be concerned about, would be the stereochemistry in our products. Note we're looking at the BRs being trans to each other. HBr as a reagent is adding of acid forming a carbocation. That carbocation could be attacked from above or below, which would mean I would get a giant mixture of reagents, not just those 2. Suggests HBr is potentially problematic. So now I could go through and look at the rest of these to see what's going on with those. That HBr process, again, backtracks out to Br2 and H2. Looking through these reagents, I've got H2, I didn't color code them conveniently, followed by Br2. I've got Br2, Br2, H2, and I get this kind of goofy one in there. So what we're talking about is the addition of H2 and Br2 across those pi bonds, but I have to get a very particular stereochemistry. Okay? That's going to be particularly problematic. Okay? D, the addition of Br2, well actually, it's not going to work out great there. All 3 answers give me Br2, and those Br2 should add anti to each other. I know they add anti to each other because I know from my reactions, or from my alkene reactions, that we would form the bromonium ion intermediate, which causes the other bromine to go in the backside. That works from an alkene. I've got an alkyne. If I did Br2 right out of the gate, what would happen? That's not going to necessarily get me my anti-alignment, and that could be a little bit weird. That would immediately then push me away from doing the Br2 first, because I want that H2 to force, or I want that forced anti-alignment. That means I should reduce first. Extra obnoxious, when I go through and do that reduction, I have to be aware of the 2 reagents here. Okay? Sodium and ammonia, or H2 and Lindlars. Okay? Both of those are distinct from H2 and platinum. H2 and platinum does a full reduction. In D, it didn't matter because I had already removed the alkene theoretically. So the full reduction there is just the alkene down. That makes sense. Okay? In B and C, it's not a full reduction. What we're doing is converting our triple bond into either the cis double bond or the trans double bond. Why would that matter? The product shows that stereochemistry, so this is where I'd have to be really careful approaching that stereochemistry to ensure that I've got my anti-alignment all the way through that, with, in particular, the alignment of my secondary groups. Okay? Full disclosure, after all that work, I would say F this and move on. Okay? Because that's going to require a very careful approach to doing each of those steps to ensure I get my cross-reference all of my pieces. Does that make sense? Presumably, I'm not allowed to actually say that for the sake of this stupid question, which means if we navigate through, I would pick one of these, either the cis or the trans, and hope for the best. Okay? I've drawn a whole bunch of stuff over the top. Since I've got tracing paper on the exam, what I would do is just shift the tracing paper off so that I could see my structures a little bit better when we're talking about the bromine addition across this. I can get my bromine up or my bromine dashed. And now I would play the game of, does this look like one of my answers? And I could just as easily have gotten the bromine down and the other bromine up. Again, playing the game of, does this look like one of my answers? And of course, I drew that one a little bit off. Do you see it? I would hope you see it, because I don't see it. Looking at my answer choices, they've conveniently done a rotation, and I've conveniently drawn it in an orientation that doesn't align very nicely. The top one looks the best. I've got the bromine dashed, the hydrogen wedged on the left-hand side, and the right molecules. Everybody see that? Talking about here aligning to here. We look on the right-hand side of that. I've got my methyl solid. I don't have the methyl solid up there. I have the methyl dashed. Conveniently, we did some bond rotations. So what I would try and do is a bond rotation to get that into alignment. Okay, to rotate that hydrogen into the plane up is going to cause all sorts of other things to rotate out. It's going to push the hydrogen dashed, and it should keep the bromine wedged, which does match. Does the bottom one match also? If I take a look at the bottom one, I've got my bromine dashed. Bromine dashed. I have a, hydrogen. Did I put the hydrogen there? I did put the hydrogen there. Hydrogen there. I just screwed the stereochemistry on that one. Did I? Stereochemistry sucks balls. Ooh, that was recorded. That should be correct there. Bromine to that side, hydrogen, yeah, I believe that's correct. I gotta keep zooming out, see my drawing. I want to rotate, I gotta do all sorts of rotations on that, don't I? Can I just flip the whole molecule over? Not quite. That doesn't align with that. Because that doesn't align, I would definitely call best of luck. That was running it with the syn addition. Syn addition was C. I'd put B and hope for the best. Would argue we've sunk so much time into that already. It's not worth the trouble. Are there other approaches to it? I'm sure. They involve lots of memorization. Are you at the lots of memorization?
Did you say C or B?
I think I said B. Because the cis gets me the syn addition right there.
What does?
B or C gets me, and the labeling is also throwing me off.
Gets me.
The C gets me the syn addition. That's the one I walked through. And I don't see those answers aligning to what was provided as my core. Because I've eliminated A and I've eliminated D, if B doesn't, or C doesn't fit, I would call B.
So sodium ammonium is a form of hydrogen solution.
So the sodium and the ammonia, which is a good question, is a hydrogen addition. That hydrogen addition is the one that sets us up with the trans product. Okay? So we can take a hot second here for reagents. Out of this, we've got H2 additions. Within the H2 addition, we have H2 and platinum. We have H2, did they actually say anything else? Just Lindlars. Lindlars, and then we have, where'd it go, sodium and ammonia. All of those are H2 additions. This one is not selective. This one reduces alkynes into the syn, or it does a syn addition, just like the not selective one. Those are syn additions. And then this last one is an anti-addition, which in the videos I just say you should memorize that, and it's a pretty critical one to memorize. If we see H2 in platinum, what are we going to add? H2. If we see H2 in Lindlar's, what are we going to add? H2. If we see sodium in ammonia, what are we going to add? I don't flip it. No, that looks weird. Yeah, it's a good idea to memorize that because they're going to test you on that. You can't just guess your way through that. Okay? Which would be a secondary piece of evidence that maybe it is B. Okay? We'd have to officially look at their key, and I wouldn't be surprised if I'm wrong because of all the stereochemistry stacking behind it. Does that make sense? So we get 3 addition reagents. All of those are going to be fairly important. There are other things you can see pop up for Lindlar's. Whoops. Again, discussed in the videos. Pretty much if you see H2 and a metal, you're just doing normal hydrogen addition, and it's a syn addition. If you see H2 and something else, that's when you're getting a selective addition. That's reducing our alkynes. Since it's H2, it's still a syn addition. It's still adding the hydrogens on the same side of the pi bond. Kind of, sort of? Not the button. There it is.
Can you see lithium instead of sodium?
As far as this anti-addition, what's critical here is the identity of this sodium. Sometimes you'll see it just written like this. In fact, ACS typically writes it like this. What we're actually talking about here is sodium metal. Okay? To show it as sodium metal, you might see Na0 in the upper right-hand corner, because what's the upper right-hand corner show based off of our Gen Chem experience? Charge. And if we have a 0, what we're saying is we have the metal form. That metal form as sodium wants to offload that electron as quickly as possible, and that's what's causing this reaction. Okay? It's a radical reaction that you will see if you go through and look at all the benzene chapter stuff, because it shows up there also. Okay? Called a Birch reduction, I believe. Okay? Would lithium also do it? Yes. Okay? Why? It has the exact same chemical properties. Why do we pick sodium over lithium? Quite honestly, I'm not positive, but I would lean towards reactivity. That lithium being smaller is probably offloading that electron a little bit faster than our sodium. So, and if it's more reactive, what does that mean? Aiden, this is in your wheelhouse. What does it mean if it's more reactive? Kaboom. If it's more reactive, it tends to be explosive, so we tend to limit our explosive. Lithium versus sodium. Okay. What are the products of this synthesis? And note, what do we see again? We see that reagent immediately come out. Okay. If we've memorized our reagents, we can immediately call attention that we're going to get our alkene. Our alkene comes out trans. It is the only reduction that gets us trans is with that sodium and ammonia, so I can draw out my trans product of that step. I follow that with osmium. Man, this is just full of stereochemistry. You gotta love it. Okay, our osmium tetroxide. What does the osmium tetroxide do? Oxidizes isn't a bad thing to memorize. It's a little questionable, but it is technically an oxidation. It breaks down the pi bond. You mean it does an addition reaction? So if we had like an organizational structure where we looked at individual types of reactions, we could now start to say for that particular addition reaction, what are the reagents that would be useful? Sodium and ammonia would be great because they're adding hydrogen. OSO4 is great as a reagent because it's adding something across the pi bond. If we also happen to remember this concept of oxidation, what might we remember it adding? Dang, Austin kept his mouth shut, so we don't know. So how would we figure it out? Look at your answer choices. What do you see is changing in your answer choices? Oxygen. So we are somehow adding oxygen. This does become problematic because how do we know how much oxygen to add? So we would actually have to know specifics of our reagent. Our OSO4 adds 2 OHs across a pi bond. Does it add those 2 H's trans or anti? Okay. Officially, syn or anti. Are the OHs added on the same side or on opposite sides? Okay, same side. How do we know they're added on the same side? Because when we talked about this particular reaction, we were looking at the osmium tetroxide coordinating directly to the pi bond. That has to happen on the same side, which then means the OHs must be added on the same side. Right? If we go through and look at our answer choices, you'd be like, but it doesn't show OH added on the same side. Okay, why not? I think you guys are both saying it. You're gesturing it, and I think you actually said it. They rotated it to be annoying. Okay, I full agreement in this case. I would argue they are rotating it to be annoying. Okay, officially, I don't think they always do that. I think they're increasingly starting to do that because people are trying to memorize their way out without representing that three-dimensional spatial awareness that we're supposed to have. So they did do a post-rotation. Okay. Again, what I would try and do is set up my system so that I could see what I was drawing. Okay. I need my OHs added on the same side. So OH, wedged OH. We could dash in my hydrogens. And now what I'm trying to do is draw that into alignment with what they drew. And again, I made one of the simple mistakes that I recommend you don't make. Okay? When I structured this in, what should I have looked at before I started drawing in all my OHs? The alignment of my answer choices. If we take a look at both A and B, where is the Y group, for lack of a better descriptor? There's a better descriptor, the isopropyl. Where is the Y group? Top left, where did I draw it? Bottom left. This means what I'm immediately starting with is a structure I'm going to have to do further manipulations with. So what I would do is actually pay a little bit more attention to the answer choices, which becomes harder on the iPad because I can't see everything on it. Okay, but if I'm going to try to align, I still want my trans alignment. Wedge OH, wedge OH. And without looking at the answer choices, I do want to do one more thing or be aware of, which the answer choices have hinted at. These could just as easily be dash OHs. Why? Say it again. Why do I have to worry about an enantiomer? All except because the answer choices say that. The chemistry, it's a pi bond. And what's reacting with a pi bond? P orbitals, both above and below. So the osmium could have reacted on either side. Okay? Which sets me up with those two possible products. I would then try and make an alignment match. Looking at the answer choices, I didn't need to draw that out because the structure on the left perfectly aligns. Everybody see that? This half of the molecule perfectly aligns with how it's drawn. So I didn't need to worry about that. I didn't have to draw my enantiomer. Okay, but what I do need to do is do a sigma bond rotation. That sigma bond rotation is going to come down to my preference. I think I want to preference the OH being above. So what I'm going to do is rotate that structure ever so slightly so that the OH is now up here. So it was at, now I'm just rotating it to drop it vertical. As I do that rotation, what happens to the methyl group? Comes at us, and then the hydrogen will necessarily be away. Does that align with either A or B? Or sorry, does that align with A?
Yeah.
Oh, really?
Yeah.
Oh, snap. So there's my answer. What if it didn't align with A? Then it's B and I move on. Okay? Again, so much stereochemistry buildup in it. You're down to 2 answer choices. If you show that it's not one, say it's the other and move on. You can prove it by doing more drawings. That requires more effort. Does that make sense? When should you prove it? When you have time. You may not have time, so don't worry about it. Okay? Here, we got lucky and we drew the structure exactly as was. There it was, and we move on. Make sense? Reagent list. Answer choices C and D. How do we get those? Say it again. Those are going to be best shown by our reaction with ozone. So we could say ozone as step 1. And I'll match these a little bit. I think I can match these better in a second. Yeah. Or ozone with another step 2. It's going to be the easiest way to align it. What's the difference between those 2 products? Ooh, actually. All right, one's an acid versus an aldehyde. What's the difference between those? Yeah, carboxylic acid. It's going to go back to Austin's suggestion at the very beginning. Oxidation. What we're talking about is oxidation of those reactions, and we're doing oxidative cleavage in this particular scenario. If we run that oxidative cleavage, do we go all the way to fully oxidized, maximize oxygen bonds, or do we stop part way? Okay. If we stop part way, we need a reagent that would allow us to stop part way. That's going to be ozone followed by cH236,
Yeah.
okay, or DMS. Okay. Answer choice D. We went from aldehyde to carboxylic acid, which means we fully oxidize, which means we're talking about ozone and anything other than DMS for the most part. Okay, I think there's one more for DMS. I think zinc I've seen show up there, but that's one that I would have to review. Okay, would this in purple get us answer choice D? As a hint, I walked you up to it to that would be the answer choice. Okay, except what we're saying is full oxidation. Did we fully oxidize? Aldehyde to carboxylic acid, that looks like full oxidation. Did I fully oxidize? No. What reagent gets us D? Good answer. None. Okay. No reagent is going to get us answer choice D. It's a complete non sequitur as far as an answer goes. Okay, we can't oxidize half of it fully, but the other half not. Doesn't fly. Kind of, sort of? I know I said I do reagent lists at the end. Is this okay to do it as we go? Okay. We're at least seeing the context of where those things show up. What reagents are used in this synthesis? Calling it a synthesis, well, I guess there are 2 steps. Okay. Again, with the stereochemistry, I could have picked a better random page that didn't involve so much frickin' stereochemistry, like for sure my Achilles heel. Oh, looking through our changes, okay, what I'm going to note is that they've switched some language on me, which is extra fun. So what I would probably immediately do is swap out that CH3 for an ME and that 2 carbon for ET so I can see those alignments a little bit better. Okay, and already I don't like how it's drawn there, so I'm going to redraw it. Looking at those changes, I'm looking at H's and I'm looking at OH's. Okay, being added in the course of this reaction. This could go through as H3O+, okay, as just outright H3O plus one step. None of the answer choices say that. Why not? If we did that straight acid addition, we're forming a carbocation, and what's the issue with the carbocation? Oxygen could attack from top or bottom, and we would get a whole lot more potential products. So H3O plus didn't make any sense right out of the gate, so we're looking at how I can add those things through the reaction. If we kind of piece our way through this, and they add NMO, okay? Do I know what NMO is? Okay, and the phrasing of that was very intentional. Do I know what NMO is? No, I have no clue, actually. Okay. Oh, and I ignored it in the previous question. Okay. And actually I was thinking what the other context here. So the OSO4 was the only thing I focused on. The NMO I completely ignored. What I thought it said was actually O3. I thought it was a follow-up system there. So the NMO is something that I can largely ignore if I don't know it. This has a lot to do with how we talked about OSO4 as a reagent. If you see OSO4, 2 times OH, same side. What if you see OSO4 with water? Same thing. What if you see OSO4 by itself? Same thing. What if you see OSO4 and NMO? Same thing. Okay, all of those secondary things are ultimately distractors. Okay? There is one exception to that. What if you see step 2 IO4, usually HIO4, I think. Anyone know that one? This is cleavage. So you'll do an oxidative cleavage. That's going to take you to your carbonyls. So if you do OSO4 followed by a step 2 of this periodate, that's going to do an extra step. We're not seeing that here, so we don't have to stress about it, but it is something to watch out for as a potential kind of red herring. So again, back to the scenario, I'm looking at H2 and OHs. A quick scan through the reagents, H2, the sodium and ammonia, we're looking at that trans. Okay, all of those are going through and adding H2. Okay, in our first step. The only difference between those 2 reagents is whether we were cis versus trans. Okay, so what I might do, actually, I'll tell you exactly what I would do. I would then look at the secondary reagents and notice that the secondary reagents are exactly the same as follow-ups. Okay, which means I can get away with just doing one of them. Okay, the weird reagent is the sodium and ammonia. To me, that's what I would bet they're triggering on, because most people can't predict their way through that because you don't know what it does. Okay, so where I would start would be the trans. Okay, and do that addition, and then say, what would I follow it with? Okay, well, I'm either following it with ozone or OSO4. What did ozone do? Added oxygens while at the same time cleavage. So I would add oxygens and then do what? Cleave. This pi bond disappears. Does that look like my answer choice?
Yeah.
What does it mean when I say this is cleaved? The whole thing is broken. You're right, I did. When we're talking about oxidative cleavage, what we're talking about is that entire structure in between. Okay? The sigma and double bond is fully removed. Our cheat with oxidative cleavage is this. Draw a really long double bond and then do what? Use a proper eraser out of the middle of it and put in oxygens. That's oxidative cleavage. Okay? Is that what the answer choices show? No. What does that mean?
That's not the answer. Or that's not.
C and D are officially wrong. It's really going to come down to how I'm adding the OH. Okay, so we're looking at cis versus trans through that process. Okay, I want to now add my oxygens on this while maintaining my trans, because that's what I picked here. Whoops, I didn't mean to draw the double bond again. My OH and my OH. I don't know why I decided to draw them in black, but I did. Okay. Because it's ozone, I would get two products, right? I get the enantiomer as well. Okay, so now what I want to do is align this to those answer choices. Conveniently, nothing is in alignment, so what I would have to do is a rotation to get this into alignment. If I did just a rotation of this molecule to get them into alignment, they aren't going to align perfectly or align in that kind of trans configuration, so I'm going to have to spend some time to figure out how to manipulate this so that it arranges to that proper configuration. Of course, the OH is down and to the left. Fuck. So I'm going to rotate the left side of the molecule so that my OH goes down. It was aimed at me. As I rotate that downwards to get it into the plane, that hydrogen is going to come out at me, and the ethyl is going to go away. The other OH, I'm rotating upwards, kind of up and out of the plane towards us to get my OH up there. If I do that, there's my hydrogen. There's my methyl. Everybody see it? Now it's a question of which answer choice does that align to? Or not which answer choice, which of these structures does that match to? It actually matches perfectly to the left one. Okay, what does that mean? When I did the trans formation, followed by my ozone, so if I did my trans A, followed by not the ozone, the OSO4, I get the structure on the left. What does that mean? A is my answer. For those people freaking out about stereochemistry, I know I would be freaking out in your spot, like, oh my God, that's a lot of stereochemistry on here. Not the entire exam is stereochemistry. It just happened that this random selection that we picked hit this. Make sense?
Yeah.
Okay. We're kind of at the end. But before we do that, I wanted to hit you with one more summary because we've asked for reaction summaries. Ta-da, there it is. Reaction summary, everything for this next unit. Okay, so if you're concerned about trying to memorize reagents, this is the place to potentially do it. All of those reagents are there. Pictures are absolutely fine. You also have full access to the slides. Okay, but this is everything for the next unit. Okay, all of EAS reactions. All that I think are relevant enough to worry about. There's a couple others that do show up that I don't think are on this. But I can scroll to them and I'll show you, you'll see why I didn't put them on there. If I can find them. Where are they? No, that's NAS. Is that it? No. That's the one. There it is. the named reaction sequence, the Sandmeyer. Any guesses why I didn't include that in the big list? That looks crazy. It's a bunch of extra reactions to go through and memorize. Okay, if we're looking at that reaction, while it is useful and you will likely see a question on it, you're looking at maybe a question on it. The vast majority of this exam is going to place, or the final is going to place more on dealing with these chemistries, and in particular, their activating and deactivating effects, their directing effects. Right? That's all fundamentals of resonance and electron pushing. Okay? So if you're looking at a slide to memorize for this next unit, this is a good one. If you're really feeling spunky, there's nothing wrong with that word. You could jump to the Sandmeyer reactions and you could throw those in also. Okay. For me personally with the Sandmeyer, I don't know why I'm still talking because I can't shut up. Sandmeyer, what I'm looking for is that N2. Okay, if I don't see the N2, I'm looking for the NH2, NO2, okay, which is going to get me to that N2 system. After that, what do you notice about all of our reagents?
They both have a,
The last.
They're all pretty much a one-for-one match for what's going on there. So if you just recognize you've got that amine and the NO2, or you see N2, it's whatever functional group shows up in the reagent shows up in your structure. Okay, in that spot. So it's a full substitution. So that's why I don't spend a lot of time trying to memorize that one. I'll just answer it as the question appears. Okay, now I'll shut up.